we're going to calculate the integral along C of f dotted with t ds, but we're going to do it by switching to a surface integral. So just to remind you, we were given originally this surface S, which was a portion of a cone, and we had determined that its boundary curve C was this circle in the plane x equals 4. Okay. And it was oriented clockwise if we looked at it straight on. Okay. So in the last video, we calculated this as a line integral, and we got 16 pi, so we're very much hoping that that's what we get when we do it as a surface integral instead. Now, I could work with the surface I was given, which was this portion of the cone. Not crazy about that, because while it's kind of nice that x is a function of y and z, remember that square root in there? The partial derivatives of x are going to have a square root of y squared plus z squared in the denominator. That's going to be undefined if y and z are 0, but y and z are going to be 0 because the origin is a part of that surface. So I couldn't use that parametrization. Now, I could parameterize the cone differently. I could basically sort of modify cylindrical coordinates. In cylindrical coordinates, I describe x and y in terms of r and theta, and then let z be z. And let z be z. But if z is a function of x and y, then it's also a function of r and theta. So I could use r and theta as my parameters. Sorry, momentary brain fart there. So I could do the same thing here. I could basically describe points in the yz plane in terms of r and theta, and then x would become a function of r and theta. So it wouldn't quite be cylindrical coordinates, but it would be the same basic idea of using an r and a theta to describe things in one plane, and then letting the third variable, which in this case is x, be a function of those two things. I could do that. I don't want to, because I see something much simpler. Because I see a much simpler surface that has the same boundary curve. And that surface is just this disk of radius 4 in the plane x equals 4. So I'm going to call that S tilde. Okay. So S tilde is the disk of radius 4 in the plane z equals 4. Now, it has that same boundary curve. Let's see what way it's going to be oriented. I can take my right hand. Now, if I try to put my right hand here, oops, my fingers are going the wrong way. I have to turn my hand around in order to curl my fingers that way. So that tells me that it's going to be oriented back. Okay. And because that plane, x equals 4, is parallel to the yz plane, I can actually see then that n is just going to be negative I. It's just going to be negative 1, 0, 0. It's just going to be pointing straight back. Okay. So now I've got this very simple surface that has the correct boundary, and the boundary is oriented positively with this very simple surface. So let's do this. This is going to be the double integral along S tilde of curl of f dotted with n ds. Okay. So we're going to need to calculate the curl of f. So that's del crossed with f. I left f written up here because I was afraid I'd forget what it was. So that's going to be my symbolic determinant, I, j, k, partial x, partial y, partial z, xy, 2z, y. Okay. And if I work this out, I actually only care what I'm going to get here, because I can see I'm going to be dotting it with this. Okay, let's go ahead just for practice and work out the whole thing. I'm going to get 1 minus 2, which is negative 1. Okay. In the j component, I'm going to get nothing minus nothing. And in the k component, I'm going to get nothing minus x. So I do get something that's going to drop out. This is very exciting. Okay, excellent. So I can say this is the double integral over S tilde of the curl of f is negative 1, 0, negative x, dotted with, n is just negative 1, 0, 0, and this is ds. I haven't switched from a surface integral yet to an integral. I haven't projected this onto the yz plane. I can, but I don't actually need to, because notice what happens. This is so nice. This becomes the double integral over s tilde of 1 ds. But that's the area of s tilde. S tilde was a disk of radius 4, so that's pi times 4 squared. That's 16 pi, which we knew should be our answer. Very nice. Now, if I preferred to switch this over to integrating over the projection of this onto the yz plane, that projection would just be that disk back in the yz plane. I could call that d. I could do that. I could say this is the double integral over d. Now, I'm going to go ahead and use the parameterization that x was equal to 4. Okay, so that's a function of y and z. So all I would be doing is taking this and replacing x with 4. So instead of negative x, I'd get negative 4. Then I'd want to use the non-normalized normal vector. But I know it's got to be pointing back. So I'd say that's got to be negative 1. And then what would go here is the partial of x with respect to y and the partial of x with respect to z. But if x is equal to 4, because that's the surface we're working with, then there are no y's or z's in the formula. Both of these are 0. And then I'm integrating this dA. So notice it ends up being the integral over d of 1 dA, which is the area of d, which is 16 pi. Okay? Because this is a disk of radius 4, S tilde was a disk of radius 4. So ordinarily, when I go from my surface in 3 space to its projection onto one of the coordinate planes, ordinarily there's some scaling factor that would allow me to switch from my ds to my dA. But when my surface is parallel to the plane I'm projecting it onto, that scaling factor is just 1. So you can evaluate this one, keeping it as a surface integral ds, or switching to a flat integral dA. You get the same thing either way. That's kind of neat to see.